In this video, we'll resolve the maximum likelihood estimation for the exponential distribution. We are given an exponential distribution with parameter beta, and we are asked to estimate beta by maximum likelihood estimation. Solution. For more on this topic, you need to subscribe to this channel. First, we need to know the rules for solving maximum likelihood estimation. The rules for solving it. Rules. 1. We take the likelihood function, take the likelihood function The second thing to do is to take the log. The third thing to do is to differentiate the function and equate to 0. So these are the things we'll do. We'll move over to this side. This is the function. The first thing to do is to take the likelihood function. So the likelihood function for the given PDF with parameter beta is the product sum as I running from 1 to n for 1 all over beta exponential negative x all over beta. So this is equal to 1 all over beta 1 exponential negative x1 all over beta multiplied by 1 all over beta 2 exponential negative x2 beta multiplied by, it continues like that, 1 all over beta n exponential negative xi all over beta. Now, we can rewrite our likelihood function properly. Our likelihood function will now be equal to 1 all over beta raised to the power of n exponential negative, because if we take the product sum of this, we'll have the summation of xi all over beta. So this is what we'll get. Like we said, we'll take the likelihood function. So this now becomes the likelihood function for the exponential distribution. The next thing to do, like we said here, is to take the log. Function. But before we take the log, we have to rearrange this properly so that we can be able to take the log. So we say rearranging the function. So if we rearrange this, we'll get our likelihood function to be, if this goes over here, we'll have beta into negative n exponential summation of xi all over beta, I running from 1 to n. Now, we can now take the log. Take the log. If you take the log, we'll have mean likelihood function of the given function will be equal to, if we take the log of this, we'll have negative n, because this will come over here mean beta. If we take the log of this, if we take the log of an exponential function, we get that same function, but the exponent will go off. So we get negative summation of xi all over beta, I running from 1 to n. So this is what we get when we take the log function. So the next thing to do is to differentiate with respect to beta to be able to find the parameter estimate for beta. So we'll move over to this side of the board to do that. We'll have to delete the whole of this. So delete this. For more on this topic, you need to subscribe to this channel. So now, since we have this here, we can now differentiate with respect to beta. So we say differentiate with respect to beta. Differentiate with respect to beta, we have the differential in f of x beta all over of differential beta. So if we differentiate this function here, we'll get negative n all over beta minus, for me to differentiate this function, as you see, is function on top of a function. So what we'll do, we'll use the quotient rule of differentiation to achieve this. So the quotient rule of differentiation says v du all over the beta minus u dv all over the beta all over b squared. And we have summation of xi all over beta. So this will be our u and this will be our v. Well, anything we differentiate, we'll now put it here. It will be equal to v. V is beta multiplied by the u all over the beta. The u all over the beta, since we don't have anything of beta here, it becomes 0. Minus u. U is summation of xi as I running from 1 to n, as I running from 1 to n. Then the v all over the b. The v all over the beta is 1. Differentiate this to get 1. We have v here. V, because of this square, we put our square here. So it's equal to 0 multiplied by beta is 0. So we have negative summation of xi all over beta squared as I running from 1 to n. So this is what we get when we differentiate this function. So we'll now carry this and put here to give us negative summation of xi all over beta as I running from 1 to n. So this is what we get. Now we can now rewrite our differential very well. We can write this out very well. So we'll move over to this other side of the board to do that. For more on this topic, you can subscribe to this channel or hit the notification button to get more of this. So now we have this. We can now rewrite this properly. The differential link function of our likelihood function beta all over the beta is equal to negative n all over beta. Negative multiplied by negative sign will get plus summation of xi as I running from 1 to n all over beta. Sorry, we have beta squared here. All over beta squared. So we equate this to 0. Equates to 0. So whatever we differentiate, we'll now equate that thing to 0. So we have negative n all over beta plus summation of xi all over beta squared as I running from 1 to n to be equal to what? 0. So we have negative n all over beta to be equal to negative summation of xi I running from 1 to n all over beta squared. So this will cancel this. We can cross multiply. Cross multiply. So we are just trying to get the estimate, the maximum likelihood estimate for beta. So if we cross multiply, we'll get beta squared all over beta to be equal to summation of xi all over n. So this will cancel this to the remaining bits. It then means that our beta estimate can be written as summation of xi as I running from 1 to n all over n. Of course, this is our beta estimate. And it is also equal to, like we know, this is equal to mean. So it then means that our beta estimate for the maximum likelihood estimation is equal to x bar. So for more on this topic, you need to subscribe to this channel. And this is how we can find the maximum likelihood estimation for the given exponential distribution.